heard. So let's see if I can hear myself before we get started today. Can I hear myself? Oops. Hello. I don't think I'm hearing myself. Let me check on my phone. Okay, can I hear myself? Um, okay, can I hear myself? Yeah, okay. So sound is happening on LinkedIn. So we're going to start today where we left off yesterday. I wanted to read an article, but I think I'm going to have a little less time today than I normally would have. And that's bad planning on my part. I need like admin help. We're going to start where we left off, and that's going to be with some boba and looking at stochastic gradient descent. Now, a really great course on this is Deep Learning AI. When the Coursera came out, took that course. Learned it years ago. Again, I don't typically work in deep learning applications, so it hasn't mattered. But their course on this is really good. Okay. I don't have my glasses, so it's going to be a strange evening, even though I have this big screen in front of me. It's like, okay, so we're going to be talking about how do we look at each individual pixel, because that's kind of what the computer reads. It doesn't see the image. It sees each individual pixel, and it comes up with a set of weights for each individual pixels. And the highest weights are associated with pixels that are most likely to be black in our case, because the black and white gradient. All right. So they came up with this formula just for how to know if it's 8. And you have that formula. So X is the image. W is a vector of weights. And so they run this formula and they update it. So how it works is initialize the base weights. Then for each image, use the weights to predict whether the weights are 3 or 7. And then based on these predictions, calculate if the model's good, how much loss there is, which determines how much is good. Then it calculates the gradient, which measures for each weight, how it changes, what changed with that loss, and it takes a step. And then all the weights are based on that calculation. And then you just repeat this over and over until you stop your training process, and that's kind of how it works. So, initialize it, predict, loss, gradient, step, stop. That's funny. Repeat until you stop. Mm-hmm. Now, if we look specifically at loss, which I think is probably the most important concept to understand, when they're talking about the guy he was quoting at the top, is testing the effectiveness of any current weight assignment in terms of actual performance. We need some function that will return a number that is small if the performance of the model is good. So that loss is the rate of error, and we want the smallest error possible, and that tells us how good it is. And to be perfectly honest, in some business use cases, you don't need to necessarily have the lowest loss. You need to have enough of the lowest loss that you can see the business impact. And I think that's one disconnect that research data scientists have from the business is I don't really need to get it better if it's not effectively changing the bottom line of whatever business problem I'm solving. And if we hit like 86%, and even if we went up to 96%, there's not going to be really a change in the effective business loss or gain that it's being used, like that model is being used to affect. You don't really need to update it. Okay. So here it plots this parabola. Everything's a parabola. And it scatters a bunch of plots here. So what it's going to look is as we move to across the parameters that we're measuring and the loss and go down and make adjustments in that slope. Everything's a slope, calculus, a derivative, that measure of that angle. We calculate that loss, and then we make another step when we change the weight, the direction of the slope, right? We calculate our loss and adjust again, and we keep doing that until we get closer to the lowest point of the curve, which is I call the center. And this concept has been around since the beginning of calculus, but now we're using it to optimize models. And yeah, so we optimize performance with calculus, and that allows us to quickly calculate whether the loss will go up or down based on the weight change that we made, like the parameter we decided to check on, right? The weight is the parameter in the terms we're using now. And it tells us, if you think back to a derivative, the rate of change at a certain point. And it's fun when you know what you're doing, but we're going to skip that. And we're going to go to this point. And if a function has a lot of weights that we need to adjust, so when we calculate the derivative, we won't get back that number that's a gradient for every weight. And so there's nothing mathematically tricky here, but you can calculate the derivative with respect to one weight and treat the others as a constant weight because you're checking everything across except for this one change. And that's kind of how you do it. So they have gradient calculations built into PyTorch so that you don't have to do the calculus anymore. You used to have to. I remember when I was first getting into the machine learning side of data science, they actually were coding out the calculus, like you needed to know how to code these models. Because we didn't have pandas and we didn't have NumPy. Scikit-learn, they didn't exist. They started to exist and rather quickly, but they didn't exist. Now, the adjustments that we make, and this just goes into APIs or API specific jargon of what they're talking about in context. So if we create F tensor, they find a gradient, right? Because they say this tensor of 3 require gradient, they plug it in. And then we calculate backward for the gradients, which is back propagation. We're going to calculate the derivative at each layer. And we'll see how this is done later according to them. And we'll check the gradient attribute of our tensor while we're at it. Right, you move it to the front. Move it to the front. And so if you have a tensor of 3, 4, and 10, and it requires gradient, what will that do? It summed it, which is 2xt. Oh, so 2 times everything there, which would be 6. Oh, I cannot do vector math in my head. I cannot do vector math in my head. 6, 8, 20. And this is the size of the vector, I'm guessing. Actually, I'm not sure what we're referring to. It does return 2 times 3, 2 times 8, and 2 times 20. Actually, let me make this bigger, because I am half blind. And that gives us the slope at a given point. So if you've already run like basic machine learning models, then you know there's this thing called a learning rate. And that's how quickly the model should learn something. And in this case, the way it's calculated is going to be that rate times the gradient. And honestly, you can set it individually, but I'm actually glad they have a learning rate learner finder in this book, because I feel like you'd just be typing in a bunch of numbers for a very long time trying to figure out what to set your learning rate at to make it optimal. And it just, if you can do it for it, it's kind of like we don't need, we can run a model to determine feature importance now, and that really wasn't something that we used to do. It saves time. You don't have to make guesses at your parameters. And that's kind of the optimization step. So when we optimize the learning rate, that is the optimization step. So we want to pick our parameters to minimize the loss as the function moves. And we don't want it to grow too small, slowly, and we don't want it to go too quickly and it just not work. So there's some form of a sweet spot. And this is if it's too high. It just bounces. So hard to find a fresh boba place. This boba's great after a long day. Still not over. Okay. So they're going to walk us through stochastic variance. And I think I could run this code, but I actually think depending on what end of data science you're going, you might just want to pick up the deep learning AI course on this if you want to go further into like research or algorithm development or anything of that nature, um, it would behoove you to um, check out, other a more detailed explanation. So here they're going to just arrange a bunch of random integers, and they're going to kind of plot it randomly. These are all random integers. They're like arbitrary numbers. They're not real data. Actually, part of me would love to put real data in here, but I don't think today I'm going to make it happen. And actually, what I might do is, since I'm not able to do the full-time day, is skip around tomorrow to higher up chapters. Because some of this for me is, I know it, I think, but I just don't know why anymore. So I will update my learning plan. So they collect all the parameters and a separate input t. So that's speed and time. And they put params and they return t times 2. So that's a separate input t and the parameters params. Okay, and so then you're going to put your, hold on. Let's read slowly because I've had a long day and I think I'm skipping over stuff. And I can't see the screen. Glasses. So, using stochastic gradient descent, we can try to find a function that matches our observations. We can't consider every possible function, so let's use a guess that it will be a quadratic, function in the form of a times t squared plus b times time plus a constant. We want to distinguish clearly between the function's input, the time when we are measuring the coaster speed, and the parameters, the values that define which quadratic we're trying. Okay, so let's collect the parameters into one argument and thus separate input t and parameters into the function signature. So they create a function, they put inputs t, parameters, and then parameters are going to be a, b, and c. Got it, in this function there. And we're going to return a times t squared plus b times t plus the constant, which is this thing written simply. In other words, they find the best quadratic function, not the best function imaginable, which limits all of the different types of functions we put in. Great plan. I forgot I cut myself to be a purple. To find the best quadratic function, we only need to find the best values for a, b, and c, because that's the quadratic formula. If we solve for the other three parameters, we'll be able to apply the same approach for more complex functions. Okay, so we define the first, what we mean by best, by choosing a loss function, which is mean squared error. And that's kind of the most standard one you can use, but it's not always the one you should use, and that's going to vary on your problem, but it's the most common. So it takes in the predictors and the targets, and it's return predictors minus targets times squared and find the mean. And that's what mean squared error does, though this should be built into other stuff, I'm sure. So first we initialize the parameters with random values. Yep. And you make a clone. Yeah, make a clone. It saves a lot of time. And they're going to calculate the predictions. And then it's going to show the predictions so we can look and see what it is. And that is, predictions are in red and speed is going to be in blue, right? Not at all. Completely backwards, negative speeds, yeah. And so the loss, if they do put it into the loss function they created, this would be the loss, which is really, really high. Not really, really low. So now they back calculate and get out more gradients, and it's shrinking, which is good. And they do it again, and it shrinks. Oh, actually, no, they convert it. This is the conversion. And so now, this is what we have out for the new params. We're going to update it base. So they chose a new learning rate, which is really small. Learning rate times the params, grad, and the data in there. Params, data, you get the data, and the gradient is none. So we call backward on the loss, right? The loss was calculated, yes, by the mean squared error, which it turned to preds as input, which we calculated using some function. This chain function represents the mathematical composition of functions which enables PyTorch to use the calculus chain rule. Got it under the hood to calculate gradients. So this is still a high loss, but it's lower than it was before. And now the actuals versus the predicted is closer. And they basically keep repeating it until this gets low or really stops improving. So this isn't improving by much anymore. These are large step improvements. These are small step improvements. And this shows where it is now. And how many times you run it really varies by whatever model we're doing. Okay. So we already have an independent variable x. We can concatenate them with a single tensor and also change them with the matrices rank 3 tensor with the vectors rank 2 tensors by using hue, which is a method that changes the shape of a tensor. So if you change the shape of a tensor, that doesn't change the contents, which basically makes it fit whatever data we're looking at. So they get the labels for the images that they're using for 3s and 2s, and they kind of make it the rate they want and unsqueeze it. So required to return a tuple of xy when indexed. So this is the tuple that it's returning as you zip these information together. Initial parameter size. Okay. This is the parameter for a neural network, and it looks like the equation for a line, if you didn't notice. Y equals mx plus b. In this case, b is mx. Slope is actually the weight, and b is bias. Yeah, slope of a line. See, high school calculus was useful. High school calculus gets you AI jobs. Okay, so it's setting a base for the bias. And we can now calculate a prediction for one image. So they pull out that one image, they calculate the weight, they transform and calculate the sum, and they add bias. So I think it's 20. Yeah, it would be very slow because it runs on the CPU, not the GPU. So, so I need to calculate it for each image, right? It'll be very slow. So I forgot so much matrix math. I do need a refresher of matrix math, but I do know that it's calculated. Like, I get that, but like, what are the nuances? Because you can multiply those things. Ruins a lot of stuff. So here they create a function, right? And they have at, which is a matrix mass multiplier. So we're going to multiply xb times weights plus bias after you calculate these two, and then you'll train it. The first image so get out this predictions, right? That they batch did the weights, like multiplication on it. And decided the output weights a 3 or a 7. And so predicts greater than 0, float equals train y. So they're basically counting how much equals it. That's giving us a true and false. And the mean 49%. This time they're going to do the no weights and find what this would be at this point multiplied, and it's the same as if they took the mean by each item and found it. That's what it's saying. Either way, it's the same thing. So this would be if they were calculating the loss based on the whole set of confidence. So we have a loss function that measures the distance between the prediction and the actual values. And instead of having to run a list comprehension, we can just do this where function to tell us that, which is really cool. It does it for you. I think key takeaway is probably also need to read the documentation pretty, not thoroughly, but enough to know some of the basic functions if they don't go through all of them in this thing, or we'd be redoing it. And I feel like go over the ones that we use the most, but not all the ones we might need. Right, loss will go down if we change the percent target for how accurate it needs to be in order to have the right prediction. So you don't want to necessarily do that. It's actually now a sigmoid function, which, sigmoids look like a sigma. I don't remember what they do. Allows outputs of the number between 0 and 1. Okay, yeah. and it's sigmoid has a not sigmoid. PyTorch has a built-in version. That's how. Imagine having to do this like by hand 7, 8 years ago. Torture. Torture. But it puts everything between 0 to 1 for you, and a min max of this function just to graph it. So now to put it on a scale from 0 to 1, and which is useful if like you're comparing two models on two different scales. So that is sigmoided, and they're confident will work if the position, even if the positions are not between 0 and 1, because it'll weight it back to between 0 and 1. And all that is required is a higher 0 to 1 confidence, right, in that image. And I guess they want to reiterate why loss is a thing. So the key difference is that the metric is to drive human understanding, and the loss is to drive automated learning. To drive automatic learning, the loss must be a function that has meaningful derivative, so a meaningful slope or change. It can't have big flat sections or large jumps, but instead must be reasonably smooth. This is why we designed a loss function that would respond to small changes in the confidence level as you move through that function that you're looking at. This requirement means that sometimes it does not really reflect exactly what we're trying to achieve, but rather a compromise between our real goal and the function that can be optimized using its gradient. The loss function is calculated for each item in our data set, and then at the end of the epoch, the loss values are averaged and the overall mean is reported for the epoch. Metrics, on the other hand, are numbers that we really care about. These are the values that are printed at the end of each epoch that tell us how our model is really doing. So we focus on those rather than the loss when judging the performance of a model. So, we want to consider the steps involved in optimization. To take an optimization step, you need to calculate the loss over one or more data items. How many should you use? The whole data set, average, single data item. Because of time, not having enough information. That's why the whole data set would take too much time, and looking at a single item wouldn't be enough information. So how do we get as precise as possible without making it unstable is kind of the question here. So instead, we take a compromise between these two. We calculate the average loss for a few data items at a time, and that is considered a mini batch. It makes sense. Take the average of a lot of different random batches. And the number of items in that batch is your batch size. You take a larger batch, and that will be more accurate, and it will stabilize your estimate, but it depends on how much compute power you have to make it not take a lot of time. So you can choose a good batch size based on the size of your data and your other constraints as you're choosing. If you have a GPU, and if you're running out of memory or not. So and then just how do we better generalize? That's how we vary things through training. So they're going to load some data, and they're going to batch in batches of 5, and they're just going to shuffle everything. Okay. And then what they're going to do, so this gives us a collection of dependent and independent variables, tuples, and this is a data set in tuples of dependent independent variables, and you can just kind of, it gives enumerates the numbers. So from all the numbers in lowercase, it assigns it a number. So there's a total of 26 values here from 0 to 25. And then if you pass those items, it creates different mini batches. So if they change to size 6, then it shuffles it. These are the batches that we get. So for those values, predict your model, look at the loss function, go backwards prompt, calculate the parameters or change parameters based on the learning rate and the gradient. And they're going to reinitialize the weights and the biases to kind of their standards. So we can do a mini batch size for testing, right? And then this is the formula from above that is just recalculating, I guess, the loss. And it calculates the gradients. And this is the tensors and the signal weights it. And so they put it all in a function, which that's what you want to do after you do everything. Just figure it out and put it into a function. And then they do for the test set. So if you call it twice without resetting, it will change based on whatever value is currently stored. That is a great note to make. So this is the basic training loop it created for each epoch that is training of the model layer. This is putting it together, and it gives it a starting point for learning rate at 1. That's big. And it just keeps, I guess, going from there until it improves how accurate it is. So this is about creating an optimizer. And you can do that with the built-in function. And they behave just like a standard Python function that you can call. So if we want to do, does the same thing int params and linear does, it's already built in. Very useful. So we didn't have to, well, I guess they're telling us how it's done, but you could just use this instead of doing what those two did and just pass in the size. And then make it available to the more parameters. And then this creates a base optimizer. So give it everything it needs, and then it's going to start taking steps. And it's going to do the zero graph. I think that's a built-in function that they have too. So I want to check to see what they're saying here. And then they create the optimizer based on the parameters that it created above and the learning rate, and it runs it through this. So training loop is now calculate the gradient, take a step, zero grad, and it'll just validate the epoch. And yeah, there's always put it into a function after you figure it out. Moral of the story. They provide in their API, not the PyTorch API, they provide stochastic gradient descent by default, and it works with PyTorch. So you also don't have to make this if you just import their package. FastAI has learn and fit, so you don't have to train the model. Very useful, or create your own learner. But if they don't have something that you want in the way you want it, you need to learn how to create your own learner. Batch accuracy, and that's just it running. Okay. non-linearity. So if there's something non-linear, you can basically write the code for a non-linear basic neural network and set it up into your calculations yourself, I guess. Both weights have to match. So this is the size, it must be 30 here and 30 here. And res max is called the, oh, it's not, rectified linear unit, ReLU, okay. And we can think and agree that a ReLU unit sounds fancy, but it's replace every negative number with a zero. There's actually a ReLU function. There's a whole math paper on it, I believe, but I haven't seen it in years. So the basic idea is that by using more linear layers, we can have our model do more computation, therefore the model for more complex function. But there's no point just putting one linear layer directly after another, because when we multiply things together, they add up to them multiple times, and that could be replaced by multiplying different things together and adding them up just once. That is to say, a series of any number of linear layers in a row can be replaced with a single layer with different set of features, parameters. But if we put a nonlinear function between them like max, then that's no longer true. Now each layer is actually somewhat decoupled from the others because it's taking that nonlinear layer in between, and it operates like an if statement. Oh, cool. So we say the composition of two linear functions and another linear function. So when we stack the classifiers, it's just without the nonlinear function, it's just the same one linear classifier. Makes sense. Amazingly enough, it can be mathematically proven that this little function can solve several computational problems in arbitrary high-level accuracy. If you can find the right parameters for W1 and W2, if you make together, wiggle the function. This is known as a universal approximation theorem. The three lines of code that we have here are known as layers. First, so we have the linear layer, the nonlinear layer, so that's just not the same one linear classifier, and then the next linear layer. Sequential is a module that will call them in turn as they run. They have ReLU, which is just the built-in version. You can set specific parameters for it and just fit the model. That's great. And it's just a supply. Looks nice. 98%. You can have as many linear layers as you want. Yep. There we can train it more quickly. So, learn the jargon, key takeaways, numbers that are calculated, with linear and nonlinear parameters, numbers that are randomly initiated and optimized. I'm sure they will talk about it more in the book. And then the rank. So you have a scalar, a vector, and a matrix, which are the rank of the tensor. So a scalar tensor is a rank 0, a vector is a rank 1, and a matrix is a rank 2. So yeah, learn the jargon. And here, actually I want to do that, but I'm not going to do it today because I have to get off. But thanks for joining. I would do the homework, and I think it would be good. Yeah, so I would do chapter 5 yourself for the next hour. It basically builds on everything that you learned and gets into model interpretation, right? How it sets up the classification graph, and it talks about the learning rate finder. And I will pick up at chapter 6 tomorrow. Sorry about the slight change of plans due to my misscheduling. But I would go through this and I might do a quick breeze over tomorrow. But we'll start tomorrow at chapter 6. Thanks for joining. I appreciate that. And if you have any feedback, let me know in the DMs or in the comment section. And we'll read the paper I wanted to read tomorrow. It's about time series LLMs. I think it would be cool. Anyway, I will see you guys tomorrow.